Welcome to this second video on 3.8 method of undetermined coefficients. We will go through a couple of examples here, mainly just to establish what the guess should look like for y sub p. So if you remember the left side of this differential equation from class, we already solved the characteristic equation, found a y sub h of c1 e to the 2t plus c2 e to the 3t. So again, you could go back to our first video from class and that would be covered in that, but hopefully that seems memorable. For our g of t, we have a polynomial here. We did do an example of one of these together in class. The nice part about our polynomial is that's not going to match any roots that we have over here since we have e raised to powers, we have exponential. So we're not going to have to worry about any repeating roots, but what we do have is a polynomial that's a quadratic. So our guess will be another polynomial that is a quadratic for y sub p. We're going to use a t squared plus bt plus c. The one we did in class was linear, so just be aware that based on the degree of your g of t, you would likely have to change y sub p. So finding the first derivative and the second derivative would look like that. Now, from here, the process is exactly the same. We would just, after we found our derivatives here, we are going to plug them in and we're going to equate our like powers. So I plug in my second derivative minus 5 times my first derivative plus 6 times our guess here. Now, kind of one of the ways that you're going to know if you did a proper guess on this is when you set it equal to g of t on the other side, you're going to start to see matching terms. So I have a t squared here plus a coefficient of 0t plus a constant of 0. So we can keep those things in mind. It has the same essential structure. If you start simplifying what you have on the left and you are not getting like powers, sorry for the interruption, and you're not getting like powers and you're not able to set coefficients equal to each other, chances are you should go back and reevaluate the guess that you used here. So I'm going to equate my like powers. I'm going to kind of do two steps in one just because, I can. So I see that I only have one t squared term here. I'm going to go ahead and just call that 6a that is being multiplied by my t squared term. I only have the one on the left, which makes that easy. Then I have a negative 5 being multiplied by a 2at, and then my 6 is going to be distributed to this bt. So it looks like I'm going to have a negative 10a plus a 6b that will make up the coefficient on t. And lastly, let's see, we'll do a different color here. We won't be able to see white too easily. So lastly, I have my just constants at the end. So it looks like I have a 2a, my negative 5 will get distributed to that b, and my positive 6 to that c. So we'll just include those at the end. 2a minus 5b plus 6c will be our constants. Now I line these up in descending order because that's what I have on the right-hand side. So again, this is where equating these things, I'll know if I did it correctly. So I have a t squared term that's going to match up with the 18. I have a t term that's going to match up with 0, and I have a constant term that's going to match up with 0. Now, don't think that by setting it equal to 0 means that we just wouldn't have anything at all. Again, most of the time what you're going to find is you get a system of equations that you may have to do a little work to solve. Here, if I set my 6a equal to 18, I get actually a pretty easy solution there. But that will assist me when I go to set up the rest of them, which I'm going to do that here real quick. So negative 10a plus 6b equals 0. And then 2a minus 5b plus 6c equals 0. Now you see why all of these terms were vital, because we do have an a, b, and c that we're solving for here. And so it is important that I included these terms that even had a coefficient of 0. So if I get a equals 3 right there, I'm going to go ahead and plug that in here. That'll give me negative 30 plus 6b is equal to 0. I add 30 over, I divide by 6. I get that b equals 5. And lastly, over here, 2 times a is 6, minus 5 times b, which would be minus 25, plus 6 times c equals 0. So that would give me a negative 19. Oh, I get a not so nice number for this. So c is equal to 19/6. Okay. But again, if I have a quadratic for g of t, I'm going to need a full quadratic. Again, even though I only had 18t squared as a single term for g of t, that does not mean that y sub p will match that exactly. In fact, here I notice that my y sub p is going to have all three terms, 3t squared plus 5t plus 19/6. I get a full quadratic, all three terms, okay? So don't think that just because we're doing a guess, it's going to look exactly like the g of t. This one has all the terms. So I'm going to kind of skip this last part here, but again, keep in mind you're taking y sub h plus y sub p to form our full general solution. For these next few, I'm just going to go through what your guess should look like. I won't run through the full example because again, finding the derivatives to plug in and then equating like powers, that will be the same. I'm just now going to get some where I have some trig terms in there. Things will get a little messy when you find the derivatives, but again, that's all just kind of calculus and algebra once you get to that step. It's really for this about the guess that we're using. So same left-hand side, again, when you assemble this full general solution, including that y sub h, I won't go all the way to that last step, but again, if you ran through it at the end, I'll post the notes so you can see if you got it right. All right, what I'm really interested in here is what we are going to use for our guess for y sub p. All right, so I see that I have trigonometric. Now, one thing to keep in mind for this is what we stated in class we're going to use for our trigonometric. So whenever you have a pure trigonometric, our guess for y sub p is going to look like a sine of beta t plus b cosine of beta t. That's what it'll look like. So again, as long as I don't have any repeats for my homogeneous solution, again, here I had two distinct real roots, so I'm not getting a trigonometric portion. So I got lucky. I don't have any repeated roots or anything here. So that 3 will function as my beta. I can ignore this 3 that's in front because that's just a coefficient on my sine function, okay? But I do need beta right there and right there. So this is going to look kind of like what we did with the last one. We need both terms. G of t only has a single term, but for y sub p, I need both terms. I'm going to be solving for a using a sine of 3t, and I'm going to be solving for b using b cosine of 3t. But again, because the sine and cosine of 3t did not match anything in y sub h, I don't have to worry about including an extra factor of t. Now, if it did, if I solved my characteristic equation over here on the left in order to get my homogeneous solution, and let's say I had complex roots, and part of that complex root was sine of 3t cosine of 3t, then what I would have to do is I would have to take y sub p and I would just multiply it by an additional factor of t. It's really as easy as that. I know it probably doesn't sound easy, but if you see a repeated root, just think about it like we did in section 3.4. Multiply through by that additional factor of t, and that is enough to kind of do your guesswork there. But I'm going to take that away. Obviously, on this example, we wouldn't need it. So this is what I would do as my guess. And then again, from here, I'm going to find first derivative. I'm going to find second derivative. You can see with our trig functions, that's not that big of a deal. But anytime we're including an extra factor of t when needed, we would have to do our product rule. So just keep that in mind. I'll post the solution here, and then I'll post full worked out solutions if you wanted to go through it. But what you would get when you would solve for y sub p ultimately at the end, we would get our coefficient of a is negative 1/26. So you'd get negative 1 over 26 sine of 3t. And for b, you get a positive 5/26. So it would be plus 5/26 cosine of 3t. So if you go through that whole process, solve for y sub p, that would be hopefully what you get. All right. But again, I'll post my full work up there so you can see it. All right. Last one, I just want to go through a couple here. And again, you can work through these. My worked out solutions will be posted for these as well. Without solving, find the appropriate form for the particular solution. So for this one, I did, yeah, well, we could put it together with our homogeneous. Sorry, I was just thinking there for a second. So because we don't have to solve, we're going to go ahead and just do our appropriate form. We're not going to solve for our coefficients. We're just going to plug them in. So let me solve the homogeneous over here. Y double prime plus 4y is equal to 0. Okay, solving the homogeneous portion of this for y sub h would be a characteristic equation of r squared plus 4 equals 0. So you may recognize this. This will be r is equal to plus or minus 2i. This will be not complex, but imaginary solutions, because at least for that alpha part, I get 0. But this would be a beta of 2. So for the homogeneous portion, y sub h, I would get c sub 1, and I did the cosine term first, cosine of 2t, plus c sub 2 sine of 2t for that. Again, we always want to do that piece because we don't want any of our potential guesses for y sub p over here to match with that. So now I can look at part A, where my g of t is this combination of this polynomial piece t squared times a factor of an exponential piece, e to the 3t. Now what we do, again, is just like this combo. And I wrote this down as like a special combo because we do in fact see this one the most, where we have a factor of a polynomial multiplied by an exponential. We do see that quite often. So what we generally do for our guess for that, I included it in our part 1 notes from class today, but I'll include it here as well. Our guess for y sub p, you can simplify this a little bit by just, instead of doing the polynomial guess plus the exponential guess, because these are multiplied, we can shortcut it a little bit. We can say t to the nth power, and then we include our e to the 3t, okay, because that e to the 3t didn't match with anything in our y sub h, so we're good with that. And then I'm going to go ahead and include that e to the 3t times a t squared plus b times t plus c. So that part in parentheses there should look familiar. That's what we did for our first problem. I'm multiplying it by the factor of e to the 3t to include the exponential piece. And really, this t to the nth power is only if you have repeats. So this one, I verify with my y sub h that I didn't have any repeats. So this would mean that n in this case would be equal to 0. I don't actually need that factor to the outside. But just so you know, this is close to the one that we wrote down in class today. It combines the polynomial piece multiplied by a factor of the exponential piece. We can do that. And then if you have any repeated factors, you include this t to the nth power on the outside, where maybe you make the n equal to 1 and you see if that piece will fit in and not give you any repeats, okay? So in this case, e to the 3t times that polynomial piece would be what I'm working with for y sub p. And what that means is that my general solution for y of t would include y sub h, which is c1 cosine of 2t plus c2 sine of 2t, plus what we got here for y sub p. So we discovered we don't need that t to the nth on the outside. So I'm just going to include this as e to the 3t times a t squared plus b t plus c. C. Now, if we were going through the whole process and doing this, we would obviously solve for A, B, and C like we did the previous two examples. For this, I just want the form that we're using, and you'll have some practice problems in the assignment that are like that as well. All right. Second problem, when we have a sum, okay? Now this is a little different from the last one where I had a product. I was multiplying this combo of types. Here I am summing them. I'm adding together this polynomial piece plus this trigonometric piece. Now you notice we have a repeated root right here. I have a sine 2t in this trigonometric portion. So what I'm going to do whenever there's a sum, this is actually a little bit easier. What I'm going to do for my guess is I sum my guesses. So I kind of treat them as two individual g of t's almost. I'm going to take the polynomial portion and I'm going to include a quadratic polynomial guess. So for y sub p, I'm going to include that at squared plus bt plus c. And then I'm just going to add on what I'm going to do for my trigonometric. Now, I do have to keep in mind for that piece where I'm doing the trigonometric, I need an additional factor of t. So I'm going to tack on to my y sub p here. That factor of t, we'll say t to the first, like we had t to the nth power over there. So this will be t to the first power, which should be good enough. I'm going to continue on in my alphabet here. I used ABC. So I'm going to do d cosine of 2t plus e sine of 2t. Notice how beta is still equal to 2. But this factor of t on the outside is all I needed to do in order to make this like a unique solution. Okay, we have a repeated root. We need to make it unique by including that extra factor of t. So if I were to write out my form that y of t would take, again, c1 cosine 2t plus c2 sine 2t. You could multiply through that t. A lot of times I don't because it makes product rule a little bit easier if it's just, on the outside. So you could leave it on the outside and just write this out. At squared plus bt plus c plus t times the quantity d cosine 2t plus e sine of 2t. And that's that. That's the form that our general solution would take. Let me know if you have any questions. I know it's tricky to do guesses at first, so hopefully an additional video helped a bit, but as always, let me know if you have additional questions for me.